Hi everybody, and welcome to Chapter 4, Atomic Structure. Atomic structure, and the first thing we're going to talk about is defining the atom. Okay, if I gave you a box as a gift, some people, and I said, do not open this box. How many of you would actually shake the box and try to figure out what's inside? Or maybe look very carefully, see if you could see through the wrapping paper and might see the box that it's in. So you use some way of looking into it to see what it is. So how can we see inside of things? What makes those things up? And that's what we're going to talk about in this chapter. We're going to talk about what makes things up. We're going to talk about the atom, and we're going to talk about some early concepts of the atom, going back to the Greeks, up through the 1700s with John Dalton, an English chemist. So we're going to be talking about those to start off with. So if we talk about Democritus, he was a Greek philosopher, and actually the word atom comes from the Greek word atomos. So this comes from a Greek word called atomos. And atomos was what Democritus described as a smallest particle of something. So an atom is still considered the smallest particle of an element that retains its identity in a chemical reaction. Now we'll find out that definition came about after quite a bit of growth and time in describing what an atom is. Now John Dalton was the first scientist almost 2,000 years later that coined this term once again and called it an atom. Now, these Greeks back 2,000 years ago could not actually observe these individual atoms, but they were able to propose. Now, notice the key word here is propose, because they were philosophers, okay? And philosophers, okay, would propose a hypothesis, but they would never test their hypothesis. So that's what's the difference between philosophers and scientists. Scientists actually test their hypothesis through experimentation. All right, so Democritus lived from 460 BC to 370 BC, or we usually use the acronym BCE, before the Common Era, and BCE means before the Common Era, and the Common Era is oftentimes used as AD. Okay, and so Democritus, what do you think Democritus was also famous for? If you said democracy, that is correct. So then along a while later comes good old John Dalton. And he picked up on the idea that Democritus said that atoms were indivisible and indestructible. John Dalton believed the same thing. Okay, so Democritus, his ideas lasted for a long time, although most people kind of ignored Democritus because they looked at other philosophers' ideas, but it agreed with later scientific theory, but as I said, it did not explain chemical behavior. It just said that these small indivisible particles exist. And as I said before, they did not use experimentation, because he used logic instead of the scientific method. Now, Dalton comes around towards the end of the 17th century, the 18th century, early 19th century, and he was a school teacher in England. And he also was a chemist. He was interested in chemistry. So this begins the idea of the atom in the modern era. He actually used experimental methods, and he transformed Democritus' ideas into a scientific theory. So he actually then came about and said, okay, we're going to take the idea and then we're going to end up with a scientific theory. So he's the first one to make Democritus's idea into a theory. And what he did, he studied the ratios in which elements combine to form new compounds in chemical reactions. Okay, we basically call this work that he did Dalton's atomic theory. So Dalton's atomic theory is what we're going to talk about right now. So there's a few rules to his theory, and we're going to go through each one. I usually list 5. We're going to see 4 here because the 4th one is kind of 2 put together. So all elements are composed of teeny, indivisible particles. Now that comes right from Democritus, okay? And this word is really important in Dalton's theory, indivisible. You probably say that every morning when you say the Pledge of Allegiance. What does indivisible mean? You can't break it up. That's it. You can't break it into smaller pieces. So here is Dalton's atoms. They're little spheres. All right? That's his first point. Secondly, atoms of the same element. Okay? So he recognizes this is a little bit different than Democritus now. He's saying there's different elements, but atoms in the same element are identical. So here you have element A and element B. This one's blue, this one's red, this one's smaller, this one's bigger. So he makes it a point that atoms of any element, any one element, is going to be different than other elements. So here's a picture to show that relationship. So that's point 2. Now, one of the most important things is that he realized there were compounds. And what were compounds? Compounds were a combination of elements. Okay, so he's going to say that atoms of different elements can mix together or can chemically combine. I want to use this one better because, yes, elements can mix together and they're not like these are mixed together. That's just a mixture. Notice they're not hooked up together in a chemical compound. They're just mixed together. And we do that in a simple whole number ratio. Now when that occurs, they're compounds. A mixture can be any ratio. So he's differentiating between mixtures and compounds. So compounds will combine in a simple whole number ratio. That's very, very important to chemistry today. Okay, when does a chemical reaction occur? Okay, chemical reactions occur when atoms are separated from each other, joined, or rearranged in different combinations. Now, atoms of one element are never changed into atoms of another element as a result of a chemical reaction. This is still true today. Keyword here is chemical reaction. So here is a compound that has element A and B. Notice how the A's are attached to the B's versus the mixture we saw on a previous slide. Now, one of the things I want to go back to this slide is we have simple whole number ratios. Okay, for instance, if we go back to something we've looked at before, water. I think I mentioned this to you before. H2O. That means for every 2 hydrogens, there's 1 oxygen. Well, there's also peroxide, which is a different compound. And what he's saying is, in this case, it's still true, but this relationship means multiple proportions. In other words, you can have different compounds with the same elements, but in different proportions to each other. Okay, and we'll talk about that more later this year. So how did he study these atoms? What evidence did he use to formulate his theory? This goes back to our packages. Okay, he studied the ratios. Okay, so that's the thing that he studied. He studied the ratios of different elements when they combined in chemical reactions. When you simply mix atoms, they maintain their own identity. We already talked about that when we talked about mixtures and compounds. They don't maintain their identity if they combine in a chemical reaction. So that goes back to what we learned when we study the differences between substances and mixtures. Okay, here's something that you're going to see as a question. How is Democritus' idea of the atom different from Dalton's? Think about that. Okay, remember Democritus didn't explain chemical behavior. It wasn't a scientific theory because it had no experimental support. Dalton transformed Democritus' ideas by using experimentation and started the beginning of the atomic theory. How can we look at atoms today? There are instruments we can use in the laboratory that can actually look at atoms for us. Okay, so if we look at larger amounts of elements, we can actually look at this concept. Here we have mercury in a Petri dish. Mercury is a liquid at room temperature, and it beads up into like little balls or ovals like this. And if you test at mercury, this mercury, which is very small, or this one's very small, or this one is very big, they all have the same properties, no matter the size. So you could go down to one atom of mercury, it would still have the same chemical properties and physical properties of mercury. What if we had some copper? If we grind it up into small particles, so we take a copper coin. Now remember, a penny is not pure copper anymore, so you can't do this with a penny anymore. You would get fine copper dust, and it would still be the same red color as copper. And if you made it smaller and smaller, you'd eventually get down to one particle or one atom of copper having the same chemical properties all the ways through. Okay, how small is an atom? Let's look at this. So that's a huge number. That's how many atoms you would need in a coin the size of a penny. That's huge. So we can't even gather what that size is. So let's look at some things that might help us. This is how many people live on Earth. So 7 billion. Almost 8 billion. Okay? Look at how many times 10 that is for atoms inside one penny-sized piece of copper. And how small are they? If you had 100 billion copper atoms, it would only be 1 centimeter long. That tells you how small an atom is. Now, as I said, we do have instrumentation that allows us to see atoms. And these are called scanning electron microscopes. they actually tunnel. We call it tunneling. And you can see pictures of this effect. It looks like a little bumpy surface that you can actually see the atoms. Now, you see it because it's magnified so much. Okay? But the instruments allow us to see what the atom actually looks like. So what we do is we take a beam of electrons and point it to the sample, and they are able to make magnifications much, much, much bigger than a microscope. You would never see an atom in a microscope. Now, a scanning microscope allows us to move atoms and maybe making atomic size electronic devices like circuits and computer chips. You might have heard of nanotechnology. Okay, this is a whole new field. This is a whole new field that there's colleges and university that just studies nanotech. Now, the thing with nanotech is, I remember when I was starting out as a chemist many, many years ago, this was just at its infancy. So in the last 35 years, this has blossomed into a field that people can actually make little machines. 3 chemists just won the Nobel Prize in basically nano machines. So this is the future. They might take a nanomachine when you're sick, inject it into your body, and it will repair whatever it is, and then it will be taken out of your body, pass through your body, and you'll be all good as new. So here we go. They call this a nanocar. Okay, and I just mentioned nanotechnology or nanoscale technology. That comes from the idea of nanometer. Okay, so we were talking about sizes. So a nanometer is roughly the unit we use when we're talking about the size of an atom. So atoms may run like 200 nanometers, 300 nanometers, 150 nanometers. And that's the unit that we use when we talk about the size of atoms. So that's why we call it nanoscale, atomic scale. And we're going to see uses in medicine, communications, energy, exploration of space. All these areas are going to be using nanotechnology. Fabrics, circuitry, all the things, the little teeny miniature circuits that allow you to have things like iPhones. All right, so let's look at this. If an atom has a radius of 1 times 10 to the minus 10 meters, how many of these atoms must be lined up in a row to produce a line 1 centimeter long? So what is a centimeter? A centimeter is 1 times 10 to the minus 2 meters. Okay, so that would be what? So you would need 1 times 10 atoms of a radius 1 times 10 to the minus 10 meters, because basically you would have to have, if that's the radius, you would have to find its diameter, which would be double that. Oh, I didn't say, oh, I'm sorry. It wasn't 1 centimeter, it was 1 meter. Okay, that makes it a lot easier, the math easier. Does it make sense? So if you wanted a centimeter, this would be 1 times 10 to the 8th, okay, because you want to get to the minus 2. Okay, to summarize, Democritus reasoned that atoms were indivisible and indestructible by using experimental methods. Dalton's transformed Democritus' ideas on atoms into a scientific theory. Scientists can observe individual atoms using instruments such as a scanning microscope. Okay, here's your definitions. Turn off the video, write these down in your notebook. And the big idea from this section, atoms are the smallest particles of an element that still have the chemical properties of that element. Very important concept. Okay, we'll see you in class.